In this video, you will learn about projectile motion. Projectile motion is when the object moves with a parabolic trajectory. What does a parabolic trajectory look like? Well, it looks like an upside-down parabola, or an upside-down U. Let's look at some examples. A classic example of projectile motion is just a person throwing a ball. You can also have projectile motion when the object is launched from a high surface, like a car launching off of a cliff. Or you can have an object that is launched up a ramp or a jump. In all of these examples, the object will have a parabolic trajectory. And what's important to notice, and you can see it in our examples here with the person throwing the ball, is that the ball is not just going up or down. The ball is going up and it's moving to the right. So we have both vertical and horizontal motion. And so what this means is we are dealing with kinematics in 2 dimensions. So when we were learning kinematics in 1 dimension, we saw objects that would move to the right or to the left, or objects that would move up or down. This motion only moved along one axis at a time. But if we're trying to visualize kinematics in 2 dimensions, we have to draw both the x and the y axis, because the object is moving horizontally and vertically. So when we visualize projectile motion, we see that we have a y component, which represents our vertical motion, so the up-down. But we also have an x component, which represents the horizontal motion, so the right-left. Let's look at our x component. This is the part of the motion that is moving our object horizontally. And this part of the motion is uniform motion. That means it has no acceleration. But let's look at our y component as well. The y component represents the vertical part of the motion. And this part of the motion is free fall motion. That means the acceleration for the y component is always equal to negative 9.8 meters per second squared. Now let's try to visualize this. We have an object that's moving with projectile motion, so I've drawn its parabolic trajectory. Now in red, I will draw the y component, and in green, I will draw the x component. And we know the acceleration for the y component is negative 9.8 meters per second squared, and the acceleration for the x component is 0. There's no acceleration. Now I want to visualize this in terms of velocity vectors. Let's start by looking at the y component. So we can see initially the object goes up because it has a velocity vector pointed up. But because it's in free fall motion, gravity slows it down until it reaches a maximum point that's the highest point of its parabolic trajectory. And at that point, the velocity of the y component is equal to 0. So what happens is the object changes direction and it starts moving down. And because of that, the velocity vectors are pointed down and the object is pulled back down to the ground. So now that we understand the y component of this motion, let's look at the x component. So the x component of this motion is what's moving the object to the right. But the x component of the velocity is constant because the x component is moving with uniform motion. Let's take a moment to look at all the variables we have for the y component and x component. Starting with the y component, we have yi, the initial position of the object along the y-axis, yf, the final position of the object along the y-axis, and we have ay, which is the acceleration in the y component, and we know this is always equal to negative 9.8 meters per second squared, and we have viy, which would be the initial velocity in the y component, and we have vfy, which would be the final velocity in the y component. Now let's look at the x component. We have xi, the object's initial position along the horizontal axis. We have xf, the object's final position along the x-axis. We know the acceleration for the x component is always equal to 0. And because we have no acceleration, there is no Vix or Vfx. We just have Vx, the velocity of the x component. It never changes. Now, what's really important to note for problem solving is that delta t is the same for both components. So delta t does not change for your x and y components. So that's a quick summary of what we just learned, but there's one more thing we have to touch on, and that's the velocity. To understand this, let's look at this example. We have the ball that was thrown into the air with projectile motion. This ball was not thrown straight. It was thrown at an angle. And because of this angle, we have Vx and Vy velocity vectors. But in most questions, you are only given v, the velocity vector that's not broken up into its components. So if we're only given v, how do we find vx and vy? Well, we have to use trigonometry. And the reason I know we need to use trigonometry is because v gets broken down into its vx and vy components. And these components form a right-angled triangle. And this right-angled triangle has a hypotenuse, an opposite side, and an adjacent side. So we can use our SOHCAHTOA to solve for the different sides. Let's start with SO, which means sine theta is equal to opposite over hypotenuse. We know opposite is Vy, and hypotenuse is V. So we can rearrange our sine theta is equal to Vy over V equation to isolate for Vy, and what we see is that the velocity in the y component, so Vy, is equal to V sine theta. Now let's solve for the velocity in the x component. We'll use cos, so we know cos theta is equal to adjacent over hypotenuse. Our adjacent side is Vx. Our hypotenuse is V. When we rearrange and isolate for Vx, we see that Vx is equal to V cos theta. Now this may seem like a lot of work, but you don't need to do this trigonometry every time. Just remember that for an object that is thrown up into the air, Vy is equal to V sine theta and Vx is equal to V cos theta. Now let's do a practice problem that will bring all of this together. Here we have a person who throws a ball from a height of 2 meters with a velocity of 10 meters per second at an angle of 30 degrees. And we want to know, how far does the ball travel? Since this is projectile motion, it has an x component and a y component. We know the x component is uniform motion, which means the acceleration is equal to 0, and we can use the uniform motion equation, which says Vx is equal to delta x divided by delta t. And we know Vx is equal to V cos theta. Looking at our y component, we know the y component is free fall motion. That means the acceleration is equal to negative 9.8 meters per second squared. And we know the velocity for the y component is equal to V sine theta. Now we want to solve for how far the ball travels, which would be delta x. We can use our uniform motion equation and rearrange for delta x. And we get delta x is equal to Vx times delta t. The first thing we need to do is solve for Vx. And we know Vx is equal to V cos theta. So all we have to do is plug in our values and solve. And what we find is the velocity in the x component is equal to 8.7 meters per second. So now we have Vx. But what about delta t? Well, we will use the y component to solve for delta t, and then plug it back in to this equation. In order to do that, we will need to solve for Viy, the initial velocity in the y component. All we have to do is plug in our values and solve, and we find that Viy is equal to 5 meters per second. We also know yi, the ball's initial position, which is 2 meters, and yf, the ball's final position, which would be 0 meters because the ball lands on the ground. Now, based on what we have, we can use the YF is equal to YI plus VIY delta t plus 1/2 AY delta t squared kinematic equation. All we have to do is plug in our values and simplify. And now what you have to realize is that what we're left with is a quadratic equation. And remember, quadratic equations have the form ax squared plus bx plus c is equal to 0. We're not working with x, but delta t is just the same. And we have to identify our a, b, c's. A is equal to negative 4.9 meters per second squared. B is equal to 5 meters per second. And c is equal to 2 meters. Now, in order to solve for delta t, we need to use the quadratic formula, which says delta t is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. Now notice there's a plus or minus, which means there's two possible solutions for the quadratic formula. Let's start with the minus. So we have delta t is equal to negative b minus the square root of b squared minus 4ac divided by 2a. All we have to do is plug in our values and solve. And we find that delta t is equal to 0.66 seconds. Now let's try the next possible solution. So we have delta t is equal to negative b plus the square root of b squared minus 4ac divided by 2a. Again, all we have to do is plug in our values, but this time we get a negative answer. And time cannot be negative, so that answer is not possible, and that means the correct value is 0.66 seconds. Now that was not the answer to our question. Remember, we're solving for how far the ball travels. So now we're working with the x component, and we've rearranged the uniform motion equation to say delta x is equal to vx times delta t. Remember, we solved for vx, and we found it was equal to 8.7 meters per second, and we just found that delta t was 0.66 seconds. So what we find is delta x is equal to 5.7 meters. And that's the answer to our projectile motion question. Try the other projectile motion questions that I've posted to test your knowledge.